So in a molecular compound, you've got two atoms, or three, or four, or however many, but more than one, that are bonded together by sharing electrons. So we talked about the most important electrons are the ones that are farthest away. That's because those are the ones that do all the bonding. So in water, you've got this big red sphere is an oxygen atom. The two blue spheres are hydrogen, right? So everyone kind of knows that hydrogen and oxygen. And so each bond in between, the one bond between each, is one electron. And so that's how they bond these things. And so that's why we write it H2O, because there's two hydrogens, one oxygen. That's easy. Now, other things are not quite so simple, or I guess maybe even more simple. Salt, for instance, just table salt, is, anyone knows, it's NaCl, right? It's sodium chloride. Yeah. And so those are actually not the same, because you get those big crystals of salt, right? And you kind of just break them in half, and they always kind of form nice cubes and things. What happens there is that you've got sodium atoms, which have one electron in their outermost shell, and chlorine atoms, which have 7 electrons in their outermost shell, and are only missing 1. So the chlorine atoms really want an electron, and the sodium's like, he's kind of lonely out there anyway, so he just gives it. So the sodium just gives the electron to the chlorine, and so now you've got chlorine has an extra electron, so it's got a -1 charge, right? Because an electron is a -1 charge, and the sodium has got 1 too few electrons, so it's a +1 charge. And so they just hang out together, and they form these really nice patterns. You can see that that's chlorine and that's sodium, maybe the other way around. Anyway, they form these really nice patterns of elements, or of ions rather, and that's what we call ionic, because it's just a donation. One chlorine needs an electron, and sodium's got an extra one, so he just gives it to them. Whereas water is not quite like that. It's more of a sharing thing. How do we know all this? How do we get to an element? How do we know hydrogen? How do we know water has hydrogen and oxygen? Because I'm telling you, no, that doesn't work. So let's do an experiment. We'll start with that. Does anyone know what that is?
Carbon.
Right. You've got 12 carbons, 22 oxygens, 22 hydrogens, and 11 oxygens.
Could be water from another planet.
It's not water from another planet. That would be H2O.
Oh, it's not
Ice, still H2O.
HCl.
What that is sugar. Yeah, it's a really important one, right? You should learn that. Simple sugar, just sugar like you'd get. And I've read sugar, carbon, hydrogen, and oxygen, right? So how do we know that? I'm just telling you, carbon's a black solid. Hydrogen and oxygen are gases normally, right? Sugar is a white crystalline solid. So what we want to do is see if we can actually make it happen. If we can break up this sugar and get carbon, just this black mess, and then we could actually make this go to hydrogen and oxygen, but instead we'll just go to water, right? And so hopefully what this will show is that if we can do this, it means that these molecular solids, these compounds that are multiple different atoms, are not just like a mixture. It's not like you just take some carbon and smush in some water and you're going to get sugar. No, you're going to get watery carbon. Yeah, gross. So what we're going to do here is we're going to actually break these bonds and form new bonds and make that stuff. Acid. Now the sulfuric acid, we're not going to go into the whole reaction of it, just because it's a little bit complicated and not that well understood. But it's basically like a catalyst. It's, if we have sugar and we just let it sit, it doesn't matter how long I let it sit, it's not going to turn into carbon and, yeah, right? Carbon and water. It's just going to stay as sugar.
Sugar.
Okay, we're good. Perfect. All right. Now this is the sulfuric acid. The reason I'm not going to have him do this is because this is potentially dangerous. So we'll just leave it over here. You wouldn't want to drink it, for instance. What's that? It's actually basically what's like inside your stomach, digesting all your food. And it's like, okay, well, it turns yellow. I'm not impressed.
Oh, it's turning to
So just kind of stir it a little bit here.
And orange juice, not like
It's like orange juice. It's a little gross. Nothing, anything? I don't know. Oh, kind of a dud, huh? Well, I guess it didn't work. Oh. There it Kind of smells like a burnt marshmallow too, right? Okay, so we tried to form sugar, carbon, and water. Does anyone see any water? Does anyone know what happened to the water? It evaporated. It was steam, right? You saw all that steam come off? So what happens is it got really hot. And so if you add too much, it actually doesn't work. That's why we'll see if this one works. A lot of acid? Do you think that's going to help?
Yeah. Blow up. Just try it. But the whole thing is it. Oh, yeah. I think that it's not going to work.
Yeah, we'll see.
Is not going to work.
I think there's enough. My opinion.
Yeah, if you took a swig, you died. Instantly. Well, not instantly. You have to roll.
It's already turning carbon.
It's not because of the little stick of it. It smells good.
It smells good.
It smells like brown sugar.
It's not brown sugar, I promise. Well, anyway, we'll let that go. So does anyone have any questions on this whole thing? Yes. Are we able to turn it back into sugar? That is a great question. If I were to pour water on this, do you think it would turn into sugar?